So thanks everyone. It's a great pleasure to be here and present our work. So first of all, I would like to highlight our amazing authors with whom we've written this paper. So Mateusz Ostaszewski, Michał Bartkiewicz, Michał Zając, Razwan Paszczanu, Łukasz Kociński, and Piotr Miłoś also did some wonderful work to so that in the end we can present this paper to you. All right, so first of all, the talk will be divided into two parts. First, I will talk a little bit about the motivation for our work and well, the thinking process in this paper, and then Bartek will tell you about the ways we try the things we try to do with NetHack and what we want to do next. All right. And if you have any questions, please interrupt me at any moment. I'd be happy to answer the questions as we go. All right. Okay. So first of all, let me maybe jump through this. Let me say a little bit about us. We are employed at Ideas and CBR. This is a leading Polish AI research institution. We are based in Warsaw. And this is a recently created institution that basically gathers top researchers from Poland and other countries to work on different important tasks in AI. I am proud to say we are part of the ALICE network. So we are very happy to collaborate with other European institutes. And we have many different teams working on many different aspects of artificial intelligence, even sometimes even a little maybe applications that are not obvious, such as precision forestry and application of artificial intelligence in psychotherapy. But we also have more standard stuff. I am working in the sequential decision-making team, and Bartek is working in the LLM alignment team. Okay, and about us, well, I am a postdoc, and I am mostly interested in the topic of adaptiveness in deep learning models. That's what I wrote my PhD thesis about. But recently, and okay, by adaptiveness, I mean things like continual learning, transfer learning, but also adapting existing models to different computational paradigms. Yeah, and stuff like that. Recently, I've been interested in using state space models, so this new generation of recurrent neural architectures for reinforcement learning. And I'm also interested in applying LLMs for decision making. So Bartek is a PhD student in the LLM alignment team, and he's been working on offline and online RL. He's currently wondering how we can use LLMs in reinforcement learning, and also how to use debates to improve alignment in LLMs. And if I remember correctly, this is also something we have in common with our team. So maybe there will be some time to discuss this as well. All right, but let's get started with the actual contents of our paper and some motivation. So in our work, we try to make a convincing argument that we need fine-tuning in reinforcement learning, online fine-tuning in reinforcement learning. And the reason we think this is true is that, well, recently we got many amazing papers trying to build foundation models for reinforcement learning. So you might be familiar with papers such as Octo, where the authors train this generalist robot policy on massive amounts of robotic data. They try to imitate the behaviors in this data set through behavioral cloning. And this way, they get this model that is able to work with many different modalities in many different tasks, work with many different embodiments and so on. That's pretty cool. There is also work such as Gato, where the authors try to, again, learn from a massive offline data set of many different environments. So now the agent is capable of both performing robotic manipulation as well as playing games, as well as conversing with the user. So I would say that the main takeaway we get from those works is that offline training scales very well in decision-making problems. Like it works, it seems that this general lesson that we got from fields such as language modeling and vision also applies here. But at the same time, I would argue that there are certain problems with offline pre-training in reinforcement learning that are not present or maybe not as pressing in supervised learning in those in like large language models or vision language models. So first of all, in those cases, we are usually upper bounded by the data generating expert. So we can only get as good as the expert because we are trying to clone its behavior, right? And this is a little bit, well, a little bit pessimistic because the great promise of reinforcement learning is that we can get better and better as times go on, and there's basically no ceiling. Obviously, there are a few methods for improving the policy when we train on the offline data, but I would say we haven't seen that much evidence that it actually scales that well, or that we can that those methods are able to improve on our expert policy in a very significant manner. So here I mean things like decision transformer and offline RL. I think there's like very interesting research going on in those directions, but we still haven't seen, you know, great improvements over what the expert who generated the data can do. Okay, then we never have enough data. And I would say this is a more pressing problem in robotics, in environments such as that, because, well, it's expensive to gather more data. In case of language or vision, we have the internet, we have other means of generating more and more data, so it's not that painful. With things like robotics, well, you need to spend a lot of money to get a really big data set. Then I would argue, and this is maybe a more fundamental problem, I would argue that you can never clone perfectly. There will always be small errors because your data set doesn't cover the whole distribution, or there are some problems with the cloning optimization. And if you do not clone perfectly, then you will see some errors when you run the algorithm online. And when those errors, when we see those errors, we will go out of distribution. As we go out of distribution, we will commit even more errors, even more mistakes. And yeah, this is just this kind of downward spiral, which I think is very common in imitation learning. And another point is that I believe that with offline methods, it is hard to understand, it is more difficult to understand how your actions impact the environment. If the only thing you have is the static data set, then you cannot really tell which actions are important for the task you want to solve right now, or which links in the data are correlation and which are causation, let's say. Okay, and we argue that a potential solution for those problems is online RL fine-tuning. So hopefully it would combine the best of two worlds, because offline RL scales very, very well, which is not so true for online RL. But the other hand, it has certain issues that maybe we can solve with online RL fine-tuning. And as Bartek will tell you later, we have a success story with applying this approach. All right, so let's get to the actual experiments, to the actual things that we have in the paper. Let me start by introducing this robotic environment, and that we will use as an example of what might go wrong with online RL fine-tuning. So in this case, the robot has to perform 4 tasks within a single episode in sequence. So first of all, it has to hammer in a nail, then it has to push an object, unplug a peg, and finally push an object around the wall. So you can see those on this nice animation, those tasks go in sequence. And important thing to note here is that the episode ends if we do not succeed at a particular stage of this task. So if we cannot perform the task of hammering a nail, then we will not see the next task of object pushing, right? Okay, so here's our environment. And now let's assume that we have a model that can do the last 2 tasks, that can perform on the last 2 stages, but not on the first 2. So in this case, it can unplug a peg and it can push an object around the wall, but it cannot hammer in a nail and it cannot push an object when there is no obstacle. Okay, so assuming that, and applying this motivation that I explained 2 slides ago, well, maybe we could use online fine-tuning in order to learn this problem fully, right? We can use this pre-trained model that can basically solve half of our environment and apply it in and fine-tune it to learn the whole thing, basically. Okay, so unfortunately, if we do this in practice, then we see something like this. So here on the x-axis are the training steps, and on the y-axis we have the success rate of actually completing the whole environment. And as you can see, there are two solid lines. The orange one is training from scratch. The blue one is fine-tuning, and unfortunately, they are on the same level. Like fine-tuning is not any better than a pure pre-training in this case. And obviously this is bad. I just promised you that online RL fine-tuning will solve a lot of problems right now, and it cannot really solve even this small problem. Okay, so let's try to understand what happened here, like what's the underlying cause of this failure. Well, to do this, we can look at the performance of our model on the specific stages of our environment, right? We had those 4 stages. We can look at how good our model is at each of those stages throughout the training. So if we look at the first and the second task, so hammer and push on the top, then well, there is nothing too much worrying there. The model learns to solve both of those tasks pretty quickly, and for the push task, we can also see some positive transfer. The fine-tuning method is actually better than pure training from scratch. But on the third and the fourth task, we see something worrying. So our model, the fine-tuning model, starts from a perfect performance. So as we said, it can solve those 2 tasks perfectly, but very rapidly, its performance falls back to 0. Okay, so it completely forgets how to solve those 2 tasks. And even more worryingly, as we get to those tasks throughout the training, and we start to train on them again, we start to encounter them again in our training process, we are still no better than simple training from scratch, right? This pre-trained knowledge is really not useful at all in this case. Okay, so we could say that the model forgets the pre-trained knowledge in this case, and it is not able to find this knowledge again, to retrieve this knowledge after revisiting those tasks. And this behavior is known as catastrophic forgetting in the field of continual learning, and where if your network doesn't see some parts of your data distribution, it will quickly forget what's the correct action to take in those parts of your distribution. Okay, so let's try to formalize maybe a little bit why does it happen in practice, and we can do this by conceptually dividing the states in our environments into 2 sets. First of all, we have the closed states that are immediately available as our trajectory begins. So for example, this would be the first level in a video game. Like you start the game and there it is. You don't have to do anything to get there. And then we have the far states. So those are the states that you have to really work to get there, right? So for example, it would be like the second stage of a video game. You have to you have to solve the first stage first before you can see the second level. You have to learn something in order to get there. And in our case, we could say that the closed states are the first tasks that we do not know, and the far states are the tasks that we do know, right? So visually, it would look something like this. We have the closed states. We have a policy that cannot really go from the closed states to the far states because it cannot solve the first 2 tasks in our setting. But then it is able to go from the far states to the goal, to actually solving the environment, right? And as we start fine-tuning, since the model cannot go from the closed states to the fast states, it will not see the closed states in its data distribution at all. So due to catastrophic forgetting, we will, while we are learning how to perform on the closed states, we forget how to behave on the fast states, right? So fortunately, there is a very simple solution for that. We can just stop forgetting on the fast states. We want to protect our knowledge of how to behave on the fast states. So now again, we start with this model that doesn't know how to perform on close, that knows how to perform on far, but now in some way we protect the behaviors on far. And as we fine-tune, we get this nice situation where we are both able to learn how to go from close to far, how to behave at the beginning of the trajectories, and we keep the knowledge of how to behave later in the trajectory. Okay, so you might ask, well, okay, that's nice, but how do we actually protect our model from forgetting? Well, in this case, we use tools from the field of continual learning, which offers us many tools to protect the knowledge in the network. Usually, it is done by adding some kind of auxiliary loss to your objective or changing your optimization algorithm a little bit so that you can handle the data shifts. Okay, so the goal here is to remember the old policy pi star parameterized by theta star, and this policy is good on states that we call far states, right? So how to protect this knowledge? The simplest way is through the algorithm we call here episodic memory. If your optimization algorithm has some kind of replay buffer, then you can simply put some examples from far states in your buffer, right? And then as you fine-tune, you will see both the closed states and the far states, and you will not forget how to behave on the far states. But for this, your algorithm does need to have some kind of replay buffer. Another approach is to constrain how much the network parameters can change. So in the case of EWC, elastic weight consolidation, we try to find out how much a particular parameter, how important is a particular parameter for the performance on a given task on the far states in our case. And this coefficient Fi represents how much we believe this parameter is important. In practice, in this case, we just compute the Fisher matrix. And then we just apply this kind of weighted squared error, right? Weighted mean square error, so that the parameters that are important for the current task do not change too much. Okay. Yet another approach is behavioral cloning. So here, this idea is very similar to episodic memory, but now we gather this buffer of states. We don't have to use the replay buffer from our algorithm. We just gather this buffer of states. We write down what were the predictions of our pre-trained policy. And as we fine-tune our model, we apply this auxiliary objective where we want to keep the predictions of our fine-tuned policy close to the predictions of our pre-trained model, so that again it does not forget what are the correct behaviors on the far states. And finally, we have kickstarting, which is very similar to behavioral cloning, but now rather than having this separate replay buffer, we just use samples that are gathered online from our fine-tuned policy, right? So this is kind of dangerous because we will also try to force our fine-tuned model to remember to behave just as the pre-trained model on the parts of the state space that the pre-trained model hasn't seen. So there are some caveats with that. Okay, and this is only a small subset of continual learning methods. In practice, in CL literature, there is much more. This is just what we are using for our experiments, and we discovered it to be completely sufficient. Okay, so now equipped with those continual learning methods, let's return to our fine-tuning problem. And very quickly, we can see that things are looking better now. So the fine-tuning and from scratch approach are still at the bottom, the blue line and the dashed purple line. But then fine-tuning equipped with the EWC auxiliary objective is 2 times as good at the end of the training. And episodic memory and behavioral cloning are something like 4 times as good, roughly. So that's pretty nice to see. And additionally, if we look at this per stage performance, then you can see what happens with the forgetting phenomenon. So on the 3rd task and the 4th task, we still see a dip in the performance in some cases, but those dips are quickly, they quickly go up after a while. And with the behavioral cloning strategy, we can actually see that there is almost no dip at all. So thanks to solving our forgetting problem, we are able to truly leverage the power of our pre-trained model, right? Finally, now we can fine-tune it in a way that significantly improves the performance. All right, but well, you may ask that you may say that this is a pretty specific scenario, that we have this particular distribution shift between the pre-trained environment and the fine-tuned environment. And you might ask, okay, do we still see this problem when there is no environment shift? Because in many cases, we have the data for the environment we want to run our algorithm on. So there is no gap in this sense. Do we still observe this problem in such a case? And I would say yes. And this is also what we saw empirically in the experiments Bartek will talk about. So in particular, if you have the setting where you pre-train offline and then fine-tune online, you can see a very similar behavior, a very similar phenomenon. So again, using the same visual aid, as I said previously, in most cases, your cloning is imperfect. So you get something that is very close to the policy you want to clone, but well, there are always some errors. And in particular, when you run this algorithm in practice online, you will see that it doesn't get from the closed states to the far states as often as the expert policy, right? Because there are some errors, so sometimes we kind of diverge. We do not get to the far states. And we argue that, well, since the distribution of how much, the ratio of how many closed states you see in the pre-training and how many closed states you see in fine-tuning, since this is disturbed, we will again see forgetting, right? Because now we see fewer examples of far states, at the beginning of our fine-tuning process. And because of that, we again see catastrophic forgetting. Okay, so we might say that the limited exposure to states we previously trained on leads to forgetting in this case, right? So this is in some sense not as severe, at least in theory, as the other case I explained, but as we will show you empirically, it's also quite a significant issue. Okay, and now let's get to the second part of our talk, where Bartek will tell us about NetHack and what we discovered there. So the floor is yours.
Okay, so I think that at least some people know about NetHack here, but I guess maybe I will quickly remind others about it. So NetHack is like a roguelike game, which was created in 1987, so almost 40 years ago. And it is based on Dungeons and Dragons, and you have you play an agent which basically has like a task to descend down the dungeon, like 50 levels deep. And here we can see like one example level, and then get the dungeon and get back 50 levels to give deity the amulet of Yender you had to get, and then you can ascend into demihood. Okay, so maybe I can show you an example run here. Will this work? Okay, all right, it works. Okay, so not sure if this is visible, but I wanted to show how maybe some early game progress. So here we have an expert of the expert playing the game. So it will like traverse the different parts of the dungeon, like go to the mines, find the mine town, and after finding it, it will get back to the main part of the dungeon and do some like this puzzle where you have to push some boulders into a holes. And so as you can see here, the game is quite complex and requires like a lot of planning. The trajectories are very long. So for I think that for an average human, it's like about 100,000 actions. Okay, thank you. Okay. Slideshow. Yeah, but maybe one might ask is okay, so why NetHack is important for reinforcement learning? Like, okay, I just shown you the game where someone is playing it, and the game looks really old. You can play it in ASCII terminal. So one part is that NetHack has a clearly defined goal where you have to descend the dungeon and then retrieve the amulet. The game is long and is quite challenging for reinforcement learning agents because you have like 50 to 100,000 steps. So this is a challenging task because most of the algorithms aren't maybe like no one thought about like 100,000 step and like architecture them, because like most of the time the environments have like 1,000 steps or something like this. And other issue is that like previously one like grand challenge for reinforcement learning was like a Montezuma's Revenge, like an Atari game, but the game was solved with memorization by approach called Go Explore. And this isn't actually what we care about in terms of solving real world challenges, because we cannot do this kind of approach. So one thing about NetHack is that each dungeon is generated randomly. So you will never encounter the same layout of levels, which forces you to be more adaptive and forces you to generalize instead of memorize. And additionally, the game is really complex. You have like many actions, like essentially the keyboard is your action space, but each action you can take usually can be combined with other like items or maybe monsters. So for example, if you look at the towel is like just an item, and usually you can apply it, which means that you will remove some oil from your hands, for example, but you can also wear a towel. So then you will put it on your face to blind yourself, which can also be useful in some scenarios where you want to be blind because some monsters can be activated. And also you can even wield a tower. Maybe it's not the most effective, but it will also do some damage. And this is really unusual, I would say, in terms of games, because most of the time games have like some specific paths that the game developers assume you will do. So for example, with food, normally you can only eat it. In NetHack, you can throw food, and by throwing it, maybe you can gather a pet because the pet will eat this food. And what is also really good for reinforcement learning is that, okay, we have a very complex game, and usually when you have a complex game, the complex games are very slow to run, and you need a GPU or something to run it. But because NetHack was created like almost 40 years ago, It's written in C, and it's really, really fast. So you can easily on single like PC get like 30,000 frames per second, which is good because you can run like a lot of experiments quite cheaply. Okay. Yeah, so I also wanted to mention a NetHack challenge, which was like, I think it's from 2021. But the first place, like auto ascent, a rule-based system, is like a handcrafted, like hierarchical system of strategies and sub-strategies, and is essentially still the best algorithm we have. So it's also interesting that even after like few years, the like handwritten approach is still the best, and neural networks are still like maybe creeping on it, but still are much worse. And after the NetHack challenge, there was created a data set called NLD-AA, like from the auto ascent. And this is like over 3 billion state actions score trajectories, about 100,000 games. Yeah, so in terms of our approach to like pre-train on offline and then fine-tune with online, this suits us perfectly because we have this huge data set and we can just pre-train a model and then fine-tune it. Yeah, so, but actually, because we have the code of the auto ascent, we can gather even more trajectories, even more data. So we use the model from like a paper called Scaling Laws for Imitation Learning, where I think Jens Tulles like created a scaled version of this like behavior cloning approach. But even with scaling the data and getting like 115 billion transitions, the model only managed to get like 5,000 points on NetHack. And auto ascent for this human monk class gets about 17,000 points. So it's still like 3 times worse, which shows how good the auto ascent is and also how hard NetHack is, because to solve the game, like usually humans have like millions of points. Like you can also try to solve the game as a human while minimizing the score, which is like also some challenge. But even if you look at like normal runs, people usually will have like about 1 million points or something like this. And one like issue, maybe like a reason behind like this behavior cloning having problems with cloning expert policy is that the game is complex, and therefore auto ascent has like really complex long-term strategy, and it's hard to clone like this such a behavior cloning. Okay, so we wanted to visualize like this problem of like imperfect cloning up, the problem where you have like these closed states and far states. And because the errors of your behavior cloning agent accumulate, the agent somehow is being misguided and cannot reach like the deeper states in the trajectories. So we can see here on the x-axis the number of turns in the game. So here we have like 50,000 turns from 0. And here we can see the dungeon depth, so like from 1 to 9. And if we have a look at auto ascent distribution, we can see that it's like 2, like basically Gaussian distributions, where first the agent tries to like camp at level 1 and get as much experience as possible, and later it tries to explore deeper into the dungeon. And the cloned policy essentially gets stuck in the first phase. Sometimes it can reach a little bit deeper, but most of the time it just finish the run on the level 1 and or something like it, sometimes level 2nd. Okay, and what happens when we just fine-tune the pre-trained model with reinforcement learning? So as you can see here, the agent starts from about like 5,000 points, and it almost instantly deteriorates. And after like 500 million environment steps, the performance isn't better than training from scratch. So it's really bad. And if we apply knowledge retention methods we mentioned earlier, like we can increase the score from the 5,000 point mark to over 10,000 point mark. And what is maybe interesting here is that there is a different method. Like the different method works best than in the previous example, when we have like these subtasks and we know how to solve only the later subtask and not the first one. And there we use a method which specifically remembered how to perform on the later two subtasks and remembered only those two. It was like just behavior cloning, where we just use the data set of this like third and fourth subtask. And here we don't have like this maybe subtask. You cannot easily disentangle NetHack. There's a lot of like different behaviors, different skills you have to know, and everything is like intertwined. So here what works is like kickstarting, where you just use your pre-trained model on the data gathered by the online policy. So basically you compute KL divergence between your pre-trained model and your online policy on your online data, and ask the policy to have similar outputs to the pre-trained model. And because the pre-trained model was trained on the whole auto-ascent trajectories, so it knows like these later stages of NetHack. So it knows how to knows how to perform on these later stages. It just cannot reach there on its own. Okay. Okay, so here I can show you similar plots after we performed like this fine-tuning. So we can see that our fine-tuning plus kickstarting managed to explore deeper into the dungeon, but in a different way. So it doesn't have this the same like these two like Gaussian spots. It's more like flowing out of on the first spot. This means that we have like the agent learned a different way to perform and to maximize the score. Okay. There is also a question about the metric we use. Basically, does maximizing the score mean that our agent like made some progress in the environment? So we also plotted like additional metrics to better understand what is happening. Is our agent actually like doing something meaningful, or is it just like farming monsters to get as much points as possible? So at least in our case, I don't think that the score overall is like a very good metric we should maximize. But at least in our case, we can see a good correlation. Like if you maximize the score, then you have a higher average dungeon depth you reach in NetHack, and also like you got the more gold and more experience points. Okay. We also had some maybe funny failure cases where we plotted the most common deaths for each of the methods. So for example, there is a problem that when you run your clone policy, which is supposed to clone the auto ascent, which doesn't quit the game, it just plays the game. Like most common death here, is that the agent quits the game. So basically it gets in a position in the game where it doesn't know what to do because it's like out of distribution example, and just like trying different buttons on the keyboard, and by accident it pushes like a quit game button, like quit game combination. Yeah, so and second cause is like a lack of food starvation. So it's normal that you just die because you don't have enough food. But this means that the clone policy had problems with cloning the original like bot generating the data. And if we fine tune with kickstarting, then we can see that the quitting problem disappears because it's like a blue. And we see that the most problematic thing for our agent is lack of food starvation, and then like killed by a soldier ant or killed by white unicorn. So basically the model dies because of like some hard monsters. Okay, yeah, so I guess we come to the end of the mind presentation, and maybe I want to say like a few words about what next, what I want to do afterwards. So I think that like I would want to get like beat this auto ascent bot, and to do this I think that it's impossible to just clone it better with like behavior cloning. I think that some new paradigm or maybe some other like algorithmic view on the problem is necessary. And I think that one of possible approaches is to combine LLMs with RL. I think that it is really exciting because we could use external data, for example. So there is like a amazing resource called NetHack Wiki, where you have like about 3,000 articles or different like monsters, items, strategies, how to behave in NetHack. And if we would somehow like transfer this knowledge about the game to like an LLM who understands the text, then I hope that there's like much more efficient algorithm to behave. Like instead of just learning from scratch and gathering the knowledge from interactions, which is in NetHack really ambiguous sometimes because you don't know what you should do and you need to explore a really vast space of possibilities, then you could just use the wiki to somehow explore with a prior that, okay, so now I should try maybe this and this and this instead of just random actions. Yeah, but I think this is like an open problem. So this could be, it's possible that other approaches will be better than combining LLMs with RL. I'm not sure, like maybe if you would somehow use just an open-ended system which will try to gather as much knowledge about the game as possible, and just by maximizing the knowledge about the game, you could go much deeper into the dungeon and then just pick like this trajectory which maximizes the knowledge the best or something like this. Yeah, I think there's like a time for discussion or maybe afterwards. Okay.
You can like discuss it over the pizza, right?
Yeah, sure. Okay. Okay, so before we finish, I want to mention like a funny back story we had. So we mentioned that we started from 5,000 points when we fine-tuned our pre-trained model. But one day we had like, instead of 5,000 points, we like dropped to 3,000 points. And it was really strange for us. So we decided to just debug it, you know. Okay, so roll back to previous commit and run again. It didn't help. Okay, so then I check out even further and to a place where I had like experiment which got 5,000 points, and it also didn't work. So I decided that, okay, so I have the same singularity image which didn't change for like a half a year. So I know that this is okay, but recently on the server, like this was like an update where they changed the CUDA version from 11.8 to 12.3 or something. So maybe this impacts because the singularity image uses this CUDA. But unfortunately, it also didn't help. I also ran this on my laptop and it also didn't help, and ran some older evaluation code, it also didn't help. And basically I spent like a lot of time on this, like basically from the whole day, like maybe like 12 hours or something. And before going to sleep, I texted Jens, like the author of the pre-trained model, like, do you know what could be the issue here? I just like think this like a CUDA problem, but I don't really know. I went to sleep, and when I get up, then he said that, oh, it's a full moon today. Like, what full moon? Like, what does it mean? Okay, so yes, it was full moon, and what actually happened is that NetHack uses the real time of the game. So on the host machine, and so it was like a full moon. NetHack, based on the date, can calculate the moon phase. And if you have a full moon, then the game starts with different message and will change the behavior a little bit. So you have increased luck actually, and also you have higher probability of encountering werewolves, like were creatures in their animal form, which means that if they bite you, you can turn into like a rat or a wolf, or and this is really bad. Almost always you will die if you get bitten. Yeah, so this was like the actual reason for our like bug from 5,000 points to 3,000 points. Yeah, and it was funny because it went a little bit viral, and we had few like magazines writing about it. Yeah. Okay. Yeah, but in summary, you want to say? Yeah.
Just say a few words. Okay, so I would say that the key points are in our presentation are, well, first of all, we argue that we need online fine-tuning to harness the power of RL models. So this offline pre-training is very nice, but with this online fine-tuning, you can get much further, as we try to show with NetHack. Unfortunately, online fine-tuning in RL is plagued by forgetting, but there is a way to solve this, fortunately. And if it's done right, fine-tuning gives us very good models. So the results Bartek showed were state-of-the-art at the time of the publication. I think they are still state-of-the-art now, at least in terms of the score. And yeah, and a very important point is that NetHack remains a very challenging environment, even for debugging in this case. Right. So thank you for your attention. If you are interested, you can write us. You can find us at Twitter. You can check out our paper or the GitHub with the code base, and we'll be at the ICML next week. So do visit us and chat with us about fine-tuning, NetHack, Moon, whatever. And yeah, and also we invite you to visit our office if you are interested to see Warsaw and maybe give a talk at our office. Then here we are. So we are located in this large building on the right. I think it's actually the tallest building in the European Union. Unfortunately, our office is on the 9th floor, so not that impressive, but I guarantee the view is still pretty nice. So if you'd like to visit us, give a talk, chat a bit, we invite you. And I think that's all, right? Yeah. Okay, thank you.